Welcome to this next class of special theory of relativity. In this class we are going to start with relativistic dynamics. Now first let us try to understand what is relativistic dynamics. What does this word dynamics mean? To understand this, we will take an example of a warranty or a guarantee card that you get for certain appliances such as mobile phones, washing machines. Now in this warranty or guarantee card there are two sections if you see properly. The first section is about definitions of all the terms that are involved in this warranty or guarantee, such as customer, what is a customer, what is a company, what are the service, what is the meaning of the word service. So in this part the definitions are taken. Then it is followed by rules of the warranty. These rules are the conditions which will make this warranty work, or it will express how this warranty will work, for what period, under what conditions. Same way we have kinematics and dynamics. Kinematics is involved in defining different terms such as position, displacement, velocity, acceleration. Whereas in dynamics, as we had in warranty card, there will be conditions or the rules. Here the rules will be called as laws. These are the laws that will explain us the mechanism of motion or explain us the cause of motion. So we can compare the warranty of an appliance with this kinematics and dynamics. In warranty we have rules and first we have definitions and the rules of the warranty. Same way in motion we have kinematics, that is definition, followed by the laws which are similar to the rules that we have in warranty. Now let us try to discuss the problem with relativistic dynamics. What is the problem? That is the reason why we are discussing this dynamics. Now let us try to understand the nature of the problem with another example. You all have used helmets in your day-to-day life. We know that this helmet is very important and very essential and also compulsory by the law. When you are on the bike, it also saves your life. But once you get off the bike, the same helmet becomes a problem. You have to carry this helmet everywhere. It is a burden to you once you get off the bike. So same way, like the helmet, which is essential and is going to save your life in certain conditions, becomes a problem under other conditions. Same way, when we were doing kinematics, Lorentz transformation helped us to find the correct equations for positions, for length, for time and for velocity. The same Lorentz transformation which helped us to follow the second principle of theory of relativity, that is the velocity of light is same for all inertial frame of reference. It basically followed this principle, or it confirmed this principle and made all the concepts in kinematics follow this principle. But the same Lorentz transformation when we use in dynamics, that is on the laws of physics, it will make them relative. That is, the laws of physics, because of Lorentz transformation, will be different for different inertial observers. Now that is not allowed in special theory of relativity. It is a principle, the first principle of relativity, that all the physical laws are same in all the inertial frame of reference. So like the helmet, under certain condition it is going to save our life, and under certain conditions it is going to be our problem. Same way Lorentz transformation, which helped us and gave us the proper equations in kinematics, is going to become a problem in the sense that it is going to make the laws of physics relative in dynamics, and we are going to discuss how to overcome this problem. It is definite that we cannot ignore or eliminate Lorentz transformation. We have to work around this problem. Now let us see how this Lorentz transformation causes laws to be relative in inertial frame of reference. For that, let us take the law of conservation of momentum. As we know that in law of conservation of momentum, if external force is equal to 0, then the total initial momentum is equal to total final momentum. Now, to understand this, let us take an example. In this example, let us see first in S frame of reference. S frame is a stationary frame of reference. So, in this stationary frame of reference, let us take a mass and an object of mass m. Now, after some time, what happens is the mass explodes into two small objects of equal masses and they travel in opposite direction. Now, the initial momentum, if you try to find, will be mass into velocity, and because the initial velocity is 0, the initial momentum will be also 0. Now, if we try to find out the final momentum, that is P of F, here this velocity will be negative and this velocity will be positive. So, we will have m by 2 into v minus m by 2 into again v. That means again the momentum will be 0. That is, initial momentum is equal to final momentum. That means law of conservation is observed here. Now, let us see the same explosion from a moving frame of reference. This is S dash frame of reference. This S dash frame of reference, let us say that it moves with velocity v towards right. It moves with a velocity v towards right. Now, when we see this same explosion in moving frame of reference, this big mass m, you will see that it will be moving in opposite direction with velocity v. And when the explosion will happen, this mass which was moving towards the right and the frame is also moving towards the right. So, this mass will appear to be stationary, it will be not moving. Whereas this mass will move with, let us say, velocity w. Now, what we want to check is that whether the law of conservation is followed in this frame of reference also by using Lorentz transformations. Now, the initial momentum, if we find, the initial momentum will be mass into velocity. Now, since the velocity is towards the left, it will be minus mv, and the final momentum will be mass of this object into its velocity, let us say w. Now we are not considering it is negative w, because we will find this w by using Lorentz transformation. Now, this second mass is not moving, so we don't need to consider this. Now, we will find this w using Lorentz transformation equations. As you remember, it is u dash x, that is velocity in the moving frame of reference, is equal to ux minus v divided by 1 minus uxv divided by c square. Now, here w is our u dash x, ux is minus v. As you can see in this example, in stationary frame of reference, this same mass is moving towards the left side, therefore it is minus v. And let us replace these values. V is equal to v only, because this is the velocity of the frame, it is same. Let us replace these values. Now, w will be equal to minus v divided by, minus into minus we will get plus v square divided by c square. So, we will get minus 2v 1 plus v square divided by c square. Now, let us replace this value into this equation for final momentum, which is m by 2 into w. This will be minus m by 2, w will be 2v divided by 1 plus v square by c square. We can cancel these two. Finally, we will get minus mv 1 plus v square by c square. Now see, this final momentum is not equal to the initial momentum. Initial momentum is just minus m into v, whereas final momentum is minus mv divided by 1 plus v square by c square. So initial momentum is not equal to the final momentum in S dash frame of reference, that is moving frame of reference, where we have used Lorentz transformation to find the velocity. So in this example, we understand that when we apply Lorentz transformation equations, the laws become relative, that is different for different observers in different inertial frame of reference. So this is an example which tells you how this Lorentz transformation creates problems that we need to understand and overcome these problems to find proper ways